Hello everyone, my name is Paul, and today I will present generative diffusion approach to performing semi-supervised classification with an interesting application in a meteorological oriented problem. We'll see in a little bit what that problem is. Sorry. Okay. In this presentation, we'll begin by addressing the problem that we are tackling in this research project and its relevance. We'll continue approaching the related work to both in the semi-supervised learning general space as well as in uh, the sneaky rainfall nowcasting problem. We'll then continue with the intuition behind our proposal and present our experimental results and finalize with a discussion related to the limitations and challenges that we face and potential future work. Now, before getting into the specifics of the problem, I'll just have a quick overview of what semi-supervised learning assumes. All machine learning tasks can often be categorized based on the type of learning that is involved. Supervised learning tasks rely on labeled data, so data that has been annotated with ground truth labels to train models to resolve the tasks or the problems. Unsupervised models, on the other hand, rely on unlabeled data, so data that does not have labels, that has not been annotated, there is no ground truth to it, to extract and learn information. And semi-supervised learning comes as a combination between the two of them, where we have a large corpus of data that is both labeled and unlabeled, with the caveat that most of the data is unlabeled, and we use the signals from the labeled data to guide the learning from the unlabeled data. There are a lot of applications of semi-supervised learning, and it is a very powerful learning strategy because it allows us to make use of all the available data that we have, because we are not restricted by the fact that we do not have ground truth labels for them. And given a new data set, it also enables us to perform cost-effective labeling, because very often it is fine to just have 1% or 10% of the data labeled. There's a lot of real-world applications, and it has a very interesting hypothesis to it, which is that the goal of any semi-supervised model is to have a better performance when training on both labeled and unlabeled data, as compared to having a supervised model trained only on labeled data, because this validates that the semi-supervised model has been able to extract more information from the unlabeled data compared to the supervised model, which does not have access to the unlabeled data. Now, why is this relevant for the problem of rainfall nowcasting that you can see here? Is because this problem can be seen and modeled as a semi-supervised image classification task, where the images represent actually remote sensing data, which can be translated as grid maps. And the task will then be summarized as classifying individual grids in terms of the amount of rainfall that is predicted to happen. So here is an example of class labels of how the grids can be annotated. We have a visualization to better understand the problem. So given a geographical space, we divide the remote sensing data, the radar data, or satellite imagery based on grids, which is often done in similar problems, as you can have seen before. And we need to annotate individual grids based on the amount of precipitation that we predict will occur. That is what the model actually needs to learn to do, and that is the formulation of the task. Now, again, why is semi-supervised learning relevant here is because it enables us to update and limit the dimensions of the grid cells from smaller to larger without requiring experts to perform labeling on the new grid cells. So we can rely on a very small percentage of labeled data interpreted by meteorologists, for example, and retrain the models based on the demands. Now, in terms of related work, I'll initially talk about general semi-supervised methods. There is a lot of ongoing research effort into this field because of because of the advantages that semi-supervised learning possesses. I've listed here a few I presented, for example, co-training, where we train two different models on two different separate views of the same data set, and we then calibrate the two models together. Or, for example, noisy student, where we manipulate and perturbate the data of a system of a teacher and student models so that we ensure that the model is regularized in a consistent manner, so that given a data sample which has been perturbed in the past, we get the same prediction. For example, with blurriness or random augmentations or transformations, and other more advanced similar methods, which I've listed here a few. Now, in terms of rainfall nowcasting, there has been a broad range of methods that have been applied. For example, classic supervised deep learning approaches involving convolutional neural networks, long short-term memory network-based, or even vision transformers. Even semi-supervised deep learning approaches have been involved, given these graph neural networks, or even generative approaches such as based on generative adversarial networks. There is an element of novelty here that because the diffusion models, which have also been presented in the past track, have never been applied to rainfall nowcasting up until now. And this was part of the challenge of the research project, adapting diffusion models to this task. Now, to explain our proposal and how we managed to solve this problem, I'll give a very brief overview and over the theoretical background of diffusion models. I'll not go into too many details because they have been already presented in the past, but a diffusion model implies two different processes. A forward diffusion process takes the input data and corrupts the data iteratively by adding Gaussian noise to it up until the entire data set has been corrupted to a random noise Gaussian distribution. And an inverse backward diffusion process tries to remove the noise from those corrupted Gaussian noise samples to recover the original data set. And what this process does is that the model learns to remove this noise and basically captures the distribution of our data set. And these diffusion models have proven very potent in terms of generative aspects, currently being the state of the art in all generative tasks which refer to computer vision, such as image generation or video generation. Now, very recently, they have been extended so that we can apply diffusion models to classification and regression tasks with efficient manner and with a lot of potency, so to speak. And in this example, we try to benefit of these approaches to basically train a diffusion model, which is in nature a generative model, to a classification task and take advantage of its potency in capturing complex multimodal distributions. So our proposal is that given a space of labeled and unlabeled data samples, as you can see in this image, the dots represent unlabeled data. You can see that it mostly dominates the space. We want to learn instead of learning sample distribution, so a distribution centered around the probability of the target Y and input X, we want to learn the neighboring distribution of these samples. Why would we do that? Is because in semi-supervised learning tasks, we benefit of these assumptions that similar data samples tend to cluster together, and especially in a lower manifold, there is a continuity between data samples. So very similar data samples will cluster together. Now, if we manage to train a diffusion model to capture the distribution of the neighboring data samples, as you can see here, later on, when we sample from this model, we are capable of observing the neighboring distribution, and then we can see which label dominates in the neighboring area so that we make an even better decision and have a more robust approach. Now, to be able to achieve this, we need a semi-supervised pipeline. I have presented the one that we designed here. We initially need to perform unsupervised representation learning to train feature extractors. So basically, feature extractors represent encoders that convert the data samples in a lower dimensionality. And then For the first step, we train a simple diffusion classifier based only on the label data, which then proceeds to a training pipeline, which uses the original diffusion classifier to pseudo annotate the unlabeled data. What is very important here is that we need to be very careful with the measure of confidence. The model needs to be very confident in the pseudo labels that it has produced, because the pseudo labels are then become part of the new training dataset, and we retrain the model with each step until the model converges. And convergence is defined as having the model basically pseudo annotate the entire unlabeled dataset, or failing to annotate the entire unlabeled dataset, which is a case of non-convergence. The roadmap of the project consisted of two building blocks. Initially, we wanted to implement the framework, the training framework, and all the relevant aspects, so that we are able to validate the semi-supervised hypothesis that I mentioned at the beginning. So basically, we wanted to validate that the diffusion model is a capable method of performing semi-supervised image classification or data classification. And in the second phase, we're focusing on applying our approach on rainfall nowcasting datasets, which have more custom requirements, such as training feature extractors for the type of data that we use, which are not computer vision based images, such as pictures of clothes, for example, and running the experiments to validate the again, the hypothesis on these remote sensing datasets. Now, in terms of datasets, for the first phase, we focused on the two most widely regarded benchmarks in semi-supervised learning, the GFAR datasets with two variants, 10 and 100. The difference is between the subdivision classes, and each of these datasets is configured in a semi-supervised manner. So, for example, in here, if the original dataset has 60,000 labels and 60,000 samples, we will train a semi-supervised model using only 40 labels, or at most 4,000 labels, and the rest of the data samples are unlabeled. So generally, the highest percentage of labels is 10%, and 90% of the data is unlabeled in a semi-supervised context more often. And for the second part, we rely on publicly available remote sensing data. For the experiments for the first phase, the results have been very promising. Here I have listed the results of training a simple supervised model only on the labeled dataset and evaluating its performance. As you can see, the model is performing very poorly, especially in the situations of very few labels, because it's hard to generalize from very few data points. While our semi-supervised approach is capable of reaching near state-of-the-art performance, or even outperforming the current state-of-the-art in setups which especially are more advantageous to it. Given the assumptions that we make, that we learn the neighboring distribution, of course, it's extra challenging to learn a neighboring distribution when you have very small number of labeled data points. So basically kind of like a stress test. But we have observed very promising performance on the semi-supervised task. I have listed here an example of how we monitor the experiments. This one is a negative example of when the model failed to fully converge, which was taken from the initial set of round of experiments. As you can see here, for each iteration, we retrain a model and we monitor the amount of labeled and unlabeled data in our dataset, and how the amount of pseudo-annotated data varies from iteration to iteration. And as you can observe, the model constantly annotates more and more of the unlabeled data up until it should finalize with annotating all of the entire unlabeled data set. In the initial round of experiments, the confidence mechanism of evaluating pseudo labels was a naive approach of just looking at the softmax layer output of basically probabilistic output and picking a threshold. But we have implemented more robust approaches, which is basically sampling from the entire distribution and performing a K-majority vote on the labels, which has proven more successful and represents the results noticed here. And as you can see, part of the reason why the model does not converge is because in the later iterations, it has very low confidence in the pseudo labels that have been produced. And this is also partly motivated due to the fact that the first iteration introduced a good enough set of noisy labels, which corrupted the class distribution. So the dataset, the training dataset became pretty imbalanced. But as you can see here, even if the confidence mechanism of the pseudo labels is naive, the model is still pretty robust, and usually the pseudo labels are correct so that it does not repropagate the errors from iteration to iteration and allows for a more robust approach. Now, discussing the limitations and challenges that we faced, there are a lot of computational demands because we need to retrain the model with each iteration, and diffusion models are known to be very computationally demanding by themselves because they require a lot of parameters. And remote sensing data has been especially difficult to deal with due to the lack of open source feature extractors, as in the case of simple images where we have access to a lot of publicly open weights feature extractors. And we observed an amplified performance hit during heavy stress. Basically, when less than 1% of the data set is labeled, the model is more prone to making errors because it's hard to capture a neighboring distribution because there is not a lot of neighboring. Yeah, and that would be all in terms of the application to rainfall nowcasting. Experimentation is still in progress, but we are nearing the end of that result, and maybe next year we'll be able to present all of our results.